Hello, this is Silas Gross, and this is Lab 3, all about circuits. The purpose of Lab 3 was to collect data and better understand circuits, capacitors, and resistors utilizing loop and node rules. Some of the key terms that we're going to be using is Kirchhoff's node and loop rules. We're going to be using Ohm's law, and we're going to have some information on capacitors. For preview, for a DC circuit, the current is going to be constant, and the voltage is going to drop to 0. And when considering a circuit with a capacitor in the series, after a long while the current in the circuit will go to 0. Physics things. We're going to look at Kirchhoff's loop rule, which is the sum of the changes in V, all amount to 0. Ohm's law, I equals EMF over R. Current equals the charge that we have in the beginning, divided by resistance. Capacitor rules, the change in V is equal to the charge over the capacitance. And then current in time, the initial current is equal to, the current at some time is equal to the initial current times all of that. And pretty much we're going to find that it jumps up to 3 volts, it goes down, and then in between here at this wire, it's going to be a constant, and then it goes down again so that it meets 0. We have the total change. Alright, systems and surroundings. So for both of the parts of this lab, the system is the completed circuit, and for both parts of this lab, the surroundings is everything that's not the completed circuit. Reasonings. To get the expected values of drops from the current voltage, we must use both the loop and node rules. And the assumptions is that we assume that there's no resistance in the wires themselves for the calculation, and we assume that all the batteries are ideal and there's no internal resistance. Some of the initial conditions and then the findings and then some of the knowledge that we have is the initial conditions are we had a 47 ohm resistor and a 100 ohm resistor for the first one. We tested these, they were correct. And then afterwards we found that both resistors, the current was 19.4 milliamps. It's pretty much the same everywhere, as it should be. The voltage drop across the 100 ohms was 1.925 volts. Voltage drop against the 47 was 0.905 volts. Ammeters have 0 resistance, voltmeters have infinite resistance. Similarities and differences. We expected the voltage to drop to be equal to the EMF. Right? We had two 1.5 volt batteries. The total voltage should have been 3. We only found it to be 2.83. This could have been because the batteries weren't charged, but we tested that and saw that they were 3. And then also, we know that V equals IR. So putting these in, we get these voltages for the across the two different ones, and we find that what we found was pretty similar to what we expected. Alright, so sources of error. Everything was pretty similar, honestly. It was a pretty good finding. And the likely reason behind the differences is that the wires do have resistance, and the multimeter may not have been that accurate. For the RC circuit, we're going to make a circuit with a capacitor and a bulb in series, 2 circuits, one with the 10 ohm bulb, one with the 20 ohm bulb. We connect the circuit to the battery, measure the time it takes for the bulb to dim completely. It lights up, then it dims. Discharge the capacitor, remove the battery, connect it all back. Bulb lights up, it dims, we measure that time too, and then we repeat the entire process for the other bulb. For the analysis of this, we found that it took the 20 ohm bulb to dim completely, this long, 10 ohm this long. And then our analysis of this is we can take these, and the larger one divided by the second one. This gives us 2.02, which is around 2. This means that our expected linear increase was true. So we're saying that going from 10 ohms to 20 ohms should double the time it takes for them to charge. When charging, the bulb lit brightly, then it dimmed. When discharging, the bulb lit up faintly and then dimmed. And we ran out of time to measure, but they should have been the discharge. They should have been equal though. For the what if questions, what if there was no resistor in the series with the capacitor, and then it what if there were no resistors in the series with the capacitor? In that case, it should result in this equation. And this shows us that the current would be infinite, meaning that the capacitor would immediately charge because of this astronomical current. However, this is not feasible in real life because, as we found out, 1, wires have some resistance, and 2, since power equals current times voltage, this would mean there is an infinite power and an infinite rate of energy transfer, which is just impossible. Thank you for your time.